Oh, that was a nice heads up.
Yeah. And no, I don't see anything Firefox related.
Okay, perfect. There's just a little button that I have to stop sharing the screen, apparently. I'll keep that off in the corner.
Cool. Well, I don't know. Are you ready to go? What do we have, like
I feel
a
ready
minute
to
left
go.
or so?
Are there a bunch of people here? Am I talking mostly with you right now? Or are we just jumping
Hi,
right
I'm
into
here.
it?
Hello. Um,
Hello, all.
Here.
Oh, I heard someone, but I couldn't make out what they said.
I would probably give it like 1 or 2 minutes, but not more than that. There are already several of us.
yep.
Oh, okay, cool.
Yeah.
We can wait another minute or so just in case any other stragglers pop in.
Sounds
Okay,
good.
I'm on both my
I
laptop
think I
and
remember
the
there's a symmetric monotile now, aperiodic monotile. One that doesn't need to
symmetrical.
be like, yeah, one that doesn't need to be like flipped every once in a while to
Oh,
be
That's
aperiodic.
that's the chiral. Yeah, yeah, that's the chiral aperiodic monotile. Technically,
Yeah.
this is that monotile. This is that tile, but this is not a chiral tiling with it. This one includes both, the reflected versions. Um, I'll try not to speak too much actually about
Ah,
aperiodic monotiles because I barely understand them and the idea behind them. But uh, we can jump right in if you guys are feeling ready.
I'm down.
Brilliant. Okay. So, like all good math stories, we start with a motivating question, and this is mine. I was I was building this dresser, and I wanted to carve the aperiodic monotiles that are so beautiful upon the face of it. And basically, I just laid a paper template onto the drawers after I had built them, and then I just went over all the lines on the template with a little engraving tool, and that took a really long time. So I spent quite a while just like tracing these little line segments, um, and I was just wondering, like, it wasn't obvious if there were more horizontal lines or vertical lines. Like for a while, I was doing all the parallels and then kind of rotating to a new orientation. So I was just wondering, thinking about, what's the ratio of like vertical to horizontal line segments here? Because I don't know if anyone here knows about aperiodic monotiles, but they never repeat their orientation. The tiles themselves do not have periodic orientations, but that's not really the same thing as like the line segments between the tiles, which again, that's what I was focusing on. Um, so this was what I was doing that made me start wondering about all this. Um,
FYI,
and
we can't see your mouse, right? I don't know if you're pointing at something. Oh, now I
oh,
can. Never mind. It just
okay.
showed up.
If I start pointing at something, that's
Gotcha.
different.
No, no,
But
no, no, no. It's
no, I'm
there.
just
It's there. Never mind. I'm just
brilliant.
a liar. Wait. So are we talking about the
All good.
quantity of lines or the total distance or length of the lines added together?
Uh,
Or
that's That's technically the same thing. These are all it might look like some of these are kind of like extra long line segments,
uh-huh.
but the long ones are 2 units long and the short ones are all 1 unit long. So the count and the length, added up is basically the same thing here. Like, add 1, add 2, add 1. Does that make
Well, so
sense?
like I mean, but couldn't you have like an orientation of line where it's like always the length two lines, and an orientation of line where it's only the one lines, and that way like you don't get the same answer for the two questions?
I do not
Like
follow that
like
question. What
imagine
do you mean?
like there's orientation A,
Mhm.
angle A, at which every line segment is
Right.
like a short line that follows that orientation compared to.
Oh, in that case, you would count the actual lengths of them. If
Okay.
if there was an example of like two different, non-unit lengths, you would be
Okay,
adding the
so we're
lengths
concerned with
together.
the
I
amount of distance within within some area. Um,
Orientation. Yeah, yeah. All of
right.
this is obviously like a finite section here on the dresser, obviously. But uh, the idea extends into infinite
Mhm.
tilings and infinite constructions of line segments. We'll get into some kind of simpler examples of that as we go on. But the basically we can think about the orientations as being like vertical or horizontal, and those can be measured in like
Okay,
an angle from
cool.
horizontal
That makes sense.
essentially. So this was the motivating question. Like what in this case in particular with this tiling that I was carving, I was like, I wonder what the different orientations are. So this was me just trying by hand to solve it. And you can see here I've labeled N1 in this little area and N2 here, and then this whole thing is N3. And those are actually given right here. Let me be able to just go here. This is the tile that has all unit segments except the double. So basically, this is like N1, N2. I actually changed my indexing at some point. So here we have N1. The previous one was N0, and then so on and so on. And this goes on infinitely. The proof of aperiodicity came from the fact that this pattern could be iterated, uh, ad infinitum. It's similar to how like you could take a square and subdivide it into 4 squares
Mhm.
and then scale those 4 squares up to the original square size. That infinite process of being able to like subdivide and scale is what's happening here. But what's happening here is a lot more complicated, and unlike squares, the that main shape that's being made is
Is there
not the
some kind
same
of
as the
symmetry
tiles
that's
that are being made in.
preserved
So
between like
when I'm talking about like
resolutions of like your level of iteration?
correct, correct, yes. So there is a shape, kind of a perimeter that does remain constant, and
I see.
like a fractal,
Uh,
it gets more
Are we going to
rough
approach
and
like a
crinkly at
specific
the
area
edges.
here if we continue to iterate this? Like, is there a like a shape, like a border, an outline that we're
Uh,
gonna? Okay,
yes,
cool.
yes, yes, yes. There is a specific boundary, and my
Huh.
computer will only let me go so many iterations deep before it starts lagging. But yes, it does approach like a
Sweet.
specific area that
And
uh, yes. So
And just to
anyways,
confirm I'm following along correctly, the famous like half tile does have different sidelines, but this is a version of it where all the sidelines are the same. Is
correct. So
that
here, let me reset here. So this was the hat. The hat shape was the original aperiodic monotile, and we'll go to N1 here. Um, this these tilings are all very related
mm,
in that they are like literally continuous with one another here. So I can go from the hat to uh, uh, equilateral version, and
mhm.
there's like a
And you're
continuous
saying the one that you were doing
transformation between the
was
two.
which one?
Does that make sense?
Was the
Yeah.
Gotcha.
Was the equilateral one. So yeah, in
Mhm.
this case, literally just counting the edges is the same as measuring them
Right.
because it's like 1 unit, 2 units,
Wait,
1
so
unit,
as you
2 units, and so on. So this was what I was working on, and the section that I was carving in particular was probably like I probably just hit build super tiles like 4 or 5
Gotcha.
times and then scaled out a little bit, and I just pulled like
Okay,
a
so,
random kind of square section
um,
like this or rectangular section. So roughly speaking,
gotcha.
this is the
So
full
wait,
shape that I
if you
was
can go back there, so maybe I now understand better what you were saying earlier.
and
As you interpolate between those two shapes, you're saying you can hit a shape in there
uh-huh,
where all of the side lengths are the same, and therefore, because there exists a tile that has that property, um,
correct.
like it's not really a fundamental
And
addition to the question to ask about, um, like the distances of lengths.
correct. Yes. And the thing that I'm really wondering about is the generic, like there should be an answer to
Mhm,
this tiling of like how many horizontal lines are there, how many vertical lines are there, and so on and so on. And in all cases that are in the middle of the slider here, there are 6 total
mhm,
orientations. But at the very far ends, it drops off to just 3. And the 3 are rotated 90 degrees from each other. So here at this end, we have vertical lines and then like um, uh, 1/12 of a turn and 5/12 of a turn as the other 2 orientations. Then here
mhm.
we have horizontal and then 1/6 and 1/3 as the orientations. And I just threw out those fractions really uh, without explaining them, but we'll get to that. I have a way of naming orientations that I've started using. Um, But the question generally, the motivating question is like, what's the relationship between
Yep.
the ratio specifically of like vertical to horizontal and horizontal to this angle and so on and so on. So this was me just like counting by hand. And by the time I was counting up to 404, I was like, okay, my hand counting is not even going to be accurate enough to be helpful for me. So this was kind of a too complicated of a question, and I was like, let me try breaking it down to something even simpler. So answering a simpler question, this one's a much easier case. We have the same type of like sequence of tilings here that are recursively generated. This is the replacing one square with four
Mhm.
squares and then scaling up so that you have unit squares at all iterations, right?
Yep.
And the total number of edges here is just we're just counting vertical and horizontal, and there's the same amount. That's pretty obvious just by looking at it. Um, and this is the equation that tells you at any
Mhm.
n iteration of this process, here's how many vertical and horizontal edges we have,
Right.
right? So this is an example of like a way simpler version, and it took me quite a while to figure out this as a concept, but it's simple enough that if no one has any questions, I'll just go on to the next slightly more complicated example.
Maybe 2 to the n times 2 to the n drop plus 1, right?
No, 2 to the n
Yeah,
plus
I think the
so
plus one
so at
comes down because
n2
otherwise
here
the whole
Perhaps
thing
we
is
plus
have
just
one is
the
not
2n
supposed
plus
to be in
1
the exponent.
or 2n plus 1.
oh, you're right. Maybe I'm sorry. I'm sorry. The yeah, it should be like 4 times 5 and 8 times 9
Okay.
and so on. You're right. That plus 1 should be down. Thank you for catching that. So, anyways, these are just the sequences, right? A set of sequences of vertical orientations and horizontal, but they're the same, right? They're a constant ratio all the way to the infinite iteration. This example is slightly more complicated, where they actually approach a ratio but are never quite at the ratio. And this sequence, we start out with just a simple square, and then we add a square on the left, and we do that infinitely. So here again we have the table of orientations here and each step of this process, and I'm going to be
Mhm.
using n sub omega as the index of like kind of like the limit of iterating this rule of adding one square to the left. Um, and if we plug in omega into these equations here, then take the standard part, which I don't really know enough about hyperreal numbers to be teaching other people about, but that's what this is essentially, is like the limit here is just a simple ratio of 2 to 1. And at the previous slide here, obviously there's never a ratio of 2 to
I
1
think so.
at any point in the table, but it approaches that ratio of 2 to 1. Does that make sense?
Yeah.
Right. And you can think about it, if you had an infinitely long line of squares
Mhm.
here and you were just looking at one end of it, you could think like one vertical, two horizontals, one vertical, two horizontals, right? You would count each square as just 3 lines, and you would be doing that quote unquote forever. So there's the intuition behind like two horizontal segments for every vertical segment. And so this is an example of what it looks like when that ratio approaches a constant. Um, okay, so what do we have so far? We have sequences of constructions. These are called L systems, Lindenmeyer systems, and it's actually a very like broad category of things that I don't know very well. But you know, you basically have a rule that you iterate, a starting point that you begin from, an initial axiom, and then some kind of like fundamental unit, which is often, in this case, it's like a line segment, and then a line segment with the crook in the middle. And so you start with a triangle and you can iterate infinitely. This is just a generic example of a Lindenmeyer system. Um, Everyone understands the tables that I've been showing, where it's like the
Yep.
sequence of points or of
Wait, one sec
orientations.
before you go ahead.
Those are
Is there an
tracking
L?
for
Are you
everyone.
saying that there's an L system for the
Okay.
aperiodic
So
monotile?
all of this leads into this.
Oh, cool. Okay, I didn't know that.
Yes, exactly. There is. And actually, if I go here really quickly, I can show you guys this interactive. So these darker lines here are showing the super tiles, and the super tiles, they're not
Mhm.
actually there. But they are the um, the rule of the Lindenmeyer system. So there's some way of converting this information of the dark lines here and this fractal. It's basically isomorphic, or whatever the word is, to the
Gotcha.
hats that it maps onto. So this
Okay.
here is the
See.
information that the Lindenmeyer system applies to, and then the actual placement of the hats is kind of secondary to that, right? So back here, let me go center view,
It's a
something like
little more
that.
complicated than an L system, isn't it? Because you have multiple kinds of super tiles that map into each other.
So it is, yes, it is a complicated L system, but that doesn't, I don't think that makes it not an L system.
Okay.
It's one that I couldn't give a very good explanation on because it's so like multi-layered and multi-variable. But like the simplest L system is literally just an alphabet of letters and then a rule for iterating them. You could have like an A and a B, and then for every A you replace it with AB, and every B you replace it with BBA, right? And you could start with some string of letters and then let the Lindenmeyer system apply, right? Just iterate the rules until either they stop or don't. Um, and I'm sure that's somehow related to like the Turing halting problem, but I'm not a computer person.
Just want to chime
cool.
in and say,
Okay.
if anyone is not reading the chat, I posted a link to the Math Overflow question and answer, which shows here's how you make the L system.
Brilliant, thank you. So, anyways, yeah, we and in our tables we have like lengths of these lines and then the orientations that they're in. Foreshadowing. What does that sound like? Uh, this this is the thing. This is what I've come up with. When you generate these lists of tables, you end up with like a
Mhm.
half of polar coordinate space, right? All lines are parallel to some line in this first half of polar coordinates. And so what happens when you plot these tables is you get, like a sequence of these objects. And really what these objects are is just like a translation of the original construction. So, if you literally just translated without rotating every little segment in this whole set here, such that the parallel ones were end to end and then the non-parallel ones intersect at the origin, what
Wait,
you
so we're
end up with
sliding all the
is one of
lines to
these
the
little
origin?
objects,
Not
and
all
and
the
they can be
tiles, but
defined
all the
literally
lines?
just by the
Is that the
set of
idea?
points at their ends here, right? If you just
Okay. Gotcha.
correct, yeah, yeah. I'm not considering at all the tiles themselves. I'm only looking at sets of line segments, and obviously every tiling is a set of line
Oh,
segments.
Are we
So
sliding the
gotcha, gotcha,
that's
lines
gotcha.
to the origin, or like one line to the origin and then a parallel line to the end of it, and then we're stacking
yes,
everything
correct.
with?
That's what you would actually be doing is if they're parallel, you're putting them end to end, and basically, that's the same as just adding up their lengths.
So the
And all non-parallel segments you put the intersection at the origin. You make them intersect. So then you can take any like discontinuous set of lines, right? Like a non-connected set, and then this translation function, this parallelity function, whatever it is, would make a single continuous object out of that set of lines.
so the middle on the left represents that like sideways infinite.
Sorry, say that
The
again.
middle map on the left.
Oh, yeah.
Yeah, that one.
This
That
one.
is
See.
the uh, sideways stack of squares? Okay.
Correct. That is this exactly. This map right here is at the
That was the
infinite
top
limit.
left.
This is what the ratio
Right.
of vertical to
Cool.
horizontal lines is. That's exactly right. And then the other one, the square for four squares, I've drawn here. And these 6 lines, kind of poorly drawn in this one's case, but these 6 orientations are the 6 orientations that the aperiodic monotiles have. They're evenly spaced, and so this is the form that the answer will come in if there is an answer. If the ratio does converge
Let
towards
me
the
ask you
infinite limit,
some
then
crazy questions.
the
First
answer
of
will
all, is there
be
a reason that you expect them not
6
to
lines
be
in these
like
orientations
all
with some
equal,
relative length to one another.
or is this just we don't know, so let's find out?
Please do.
Mhm.
Um,
Is this iteration by
well, let me
iteration, like
just run
2 on the
back.
first iteration,
I
then
have
15
no
on
idea
okay.
what to expect, but you can just see here
Gotcha.
in the first 3 that I counted, like clearly these are not all the same length, right? Like 15, 10, 15.
I see. Yeah.
Yes, sorry, my commas here. You can kind of maybe see it right here, but
Mhm.
horizontal at each iteration, we have 2, then 15, then 89. So it like just obviously on the face of it, they are not just the same. It would be interesting if they were, but they're not. Um, so and I don't even know if they do converge. I have no way of knowing that they do. For all I know, they completely oscillate or are just stochastic and unrelated to one another. Um, but parallelity maps, that's a parallelity map. If I say those words, I'm referring to this like little fan. And this one down here is just like another example of a crazy one. Right? All the lines intersect at the origin, and there's a bunch of different orientations, but it's this like very simplified object. And a lot of different constructions are going to have the same parallelity map, the same ratio, right? Um, for example, all the steps here, um, different numbers of line segments, but the same ratio at all times. The same parallelity map for this
Mhm.
set here, same
Right.
parallelity map here. So it's a surjective function. There's not
Makes
actually like
sense.
a way to go from a parallelity map to the thing that it came from, to the construction that made it, but it tells you something about the original construction. Um, so here, this is a formal example in my preferred notation. I like to put the. Go ahead. Oh, I thought someone was saying something. I, as far as labeling orientations, I've just kind of made the decision that I'm calling horizontal, tau, and then a quarter turn from there is tau over 4. That's vertical. Another eighth of a turn. That's 3 tau over 8. So this is just my convention for labeling orientations. Um, and then here's the table for the Koch snowflake, and it's actually a very
Mhm.
simple equation, right? It's an extremely understandable thing that's happening here as far as the ratios. And at all levels, it's just the same ratio. So this little map right here is every step of this L system. And scaling is a huge thing in Lindenmeyer systems. So you can kind of just assume that if something looks
Wait, so
scaled weird, it's just being represented
for
that
this
way. You
aperiodic
can have all
tiling,
different kinds of
like
rules for
given a
scaling
tile, is there
embedded
a
in the
unique way
Lindenmeyer
to tile
system.
it
So
aperiodically?
yeah.
Like, are we discussing the
Um,
probability distributions of like directions given a specific tiling, or is it
uh-huh.
necessarily the only like is the answer unique? Is effectively what I'm asking up to the selection of a tile.
Mm, it is unique, but there are lots of different ways to
Mhm.
tile with the same tile, right? So the different ways to tile with the same tile is a question about the Lindenmeyer system that's being used. Because this tile right here, actually, this one that has equilateral edges, it can tile periodically if you allow for reflections. But also, as shown right here, it can tile aperiodically with reflections also.
Right.
So depending on what Lindenmayer system in particular is being used,
So
what
there are
axiom you start
multiple,
with,
just to say that back
what
to you,
rule
there are
is being
multiple
applied,
tilings
and
using
what
this tile, but
possible
we're concerned with a
options
specific
are made
one, which
available
is
in that system.
is that the
That's
only
what determines
aperiodic tiling using this tile?
the sequence that's generated, right? And yep. Uh, no, actually no, it definitely isn't, because you could tile aperiodically chirally without reflecting this tile. You could just take it and without flipping it, only rotating it, you could
Gotcha.
tile aperiodically, or as shown right here, right now,
And
you
the
can
question you're
tile
asking is the specific
aperiodically with
tiling.
reflections, or you could tile periodically.
Gotcha.
You could tile,
Right.
in a repeating way with reflections, but that's a whole different Lindenmayer system that would need to be written.
I don't know. I can't hear it.
Correct. I at least, again, in the dresser that I was carving, I took some finite subsection of this exact tile. I went to this web page here. Oh, I'm sorry. I hope that car alarm goes off. I hope it's not mine. One moment, actually. Um. So yeah, the question that I was asking in particular was like,
Mhm.
this tiling and this set of rules that are being applied here, as I click build super tiles and this tiling gets larger and larger, um, does the ratio of edges converge or of orientations converge? And if so, to what? And if not,
Right.
like, what does it do? Does it oscillate? Because it is possible for, like, you know, for some number of iterations, this one's consistently longer, and then for few more, it's this one, right? You could have
Oh,
some like bouncing effect as the number of iterations goes on. So these right here, this is N0, N1, and N2 of the original data table that I showed at the beginning, the one that I was counting by hand, and like just purely on it kind of looks that way. Nothing that would fly in
yeah.
proof. Like it feels like these are all going to creep towards the same length
Or
overall.
maybe like
Right.
But I
multiple
What's
of
don't
the
the
know.
ratio
tile
there?
over 6
And
look like they're going to
Have
approach each
you?
other, and then the others
Yeah, like
each
the
other.
ratio of the average
there's
of
two sets of triples.
the tau over, like the tau over.
correct, yes, every other orientation is very consistent, and the ratio of what? We would
Mhm.
have to we would have to average the table here. This is the data points that
Looks
I
like
use to
roughly
generate
Right.
those graphs.
4/3.
Right, ballparked, give or take.
Either 4/3 or 3/2, probably, or some irrational
So
fraction.
so that's right. Isn't it
Right.
interesting to wonder about? This is the question. This is what I'm trying to figure out. And then also there's kind of a next door question, which is going to be here. Let me start from the beginning and pick a nice low iteration here. So obviously there's some parallelity map here. Maybe even this is the parallelity map for this iteration,
Wait,
right?
wait,
For this right
wait a
here.
minute.
Um,
So hold on.
as you
Can we just
change
intermediate
between the
value
different
theorem this? Like
aperiodic
if
monotiles,
at one
there's
end
like
of
a
the spectrum here
continuous
you have you have
transformation
that
of
where
the
there's only
parallelity
3
map
possible
in
options,
accordance with that, right? You
and
can just
like on
imagine how
the
as
other
the
end of the
slider
spectrum there's 6
reduces some
possible
of these
options. Like
orientations to
on the
0.
leftmost end of the, oh sorry, 3. Oh, got you. But somewhere in the middle there's 6. Okay. In in
Uh-huh.
that case, that seems to lend a lot of credibility to the theory that the 3 alternating ones are
Uh-huh.
going to
There's
have
3 here
different,
too. There's
different
3 in both
ratios.
cases.
Because like, as you're
Yep.
further to the end of the spectrum, then you're gonna end up
Correct.
with,
And everywhere in the
like,
middle.
different
It's as
ratios
soon as you
of,
are off of that very
um
edge, now there are
yeah.
6.
Mhm.
Correct, right? Like definitely that is true. But what's not obvious is here in this, finite example, there's some like some ratio of these 3 orientations that's just a an exact value. But as
Right.
you
Sure.
tile aperiodically with this tile, which again, this tile could tile aperiodically
Sure.
or not, but right now we're talking about the aperiodic case. It's not exactly obvious that those three
Right.
orientations are
So
exactly
wait, hold on.
even. Like
I have
in
I
the
have like
infinite
10
case, what if
questions
you know it
now.
was 2
so
and 2 and
start on the right end. Can you just go to the right end and
right?
the
Like
left end? I'm curious if we
if
like
they were
immediately
slightly
get
skewed,
can
then
we
that
try the
would
left
make
end now?
the middle
Other than the
section
left.
equally skewed or skewed in the same way, you would assume.
Right.
So even
Okay, so like the leftmost ones are
oh, I'm so happy.
the
Good.
set
Let him
of
rip.
like the sets of angles that exist in the chevrons
Uh-huh.
and those in the comets are disjoint, right?
Oh, and I can just click actually between them because the far ends are called this is the chevron and this is the comet. So
Yeah. Right.
correct.
Right.
And right here we can see there's there a third. Oh, sorry, wait. This one does actually have
Mhm.
no. My
Right.
mistake. So
Okay, cool. So
the
I'm
three
curious where
orientations that we're looking
where
at
it
here
equalizes
are
in
the
the middle there.
vertical and then the two here, 5 tau over 12 and tau over 12. And then at the other far end, we're looking at the opposite 3, tau over 3, 6, and tau. So
Sounds plausible.
correct. And my assumption is that if the ratios are even in both end cases, then they're probably even in the middle
Yeah.
case where you like average the two of them. Those two even cases added together, you're going to get another even case.
Instead of
Maybe,
concerning
I don't
yourself
know.
with the
I'm hoping that you guys are going to
with
be so
the
interested in this question that you're going to
lines,
start
have you
doing work
counted up
to
the
help me
orientations
answer
of the
it.
different shapes?
But that slider, right, this
Like
continuous transformation between all these different tilings, it applies at all n, right? You could do it at any stage. So okay, I have considered this and the in tiling, the orientation of the tile itself like matters, and there are already ways of describing it and tracking it. So I think that's kind of like a known answer. I believe that the orientations come
is
in
your
an even
answer hidden in there
distribution,
then?
but
I have seen that
because
studied.
Because the answer to the question just
sorry,
does
go
it
ahead.
not just fall out of that?
I was just saying that yes, people have already calculated distributions of like flipped versus non-flipped tiles using the inflation
Exactly.
rules and eigenvalue stuff.
Right. But the orientations of the
I would think it
I was
does,
just about to
yeah.
say, not exactly, because if you rotate a tile by 180 degrees, it has the exact same parallelity. Rotating something by 180 degrees puts all of the orientations of line segments back where they started, right? So you could have
Sure.
two different orientations of tiles that lend themselves to the same parallelity map,
Is
if
there an
that
even
makes sense.
Sure.
And
distribution?
so
But that
Yeah.
being
the
Is there an even distribution of the
ahead.
It
orientations?
does matter.
no, because the flipped tile is less common, I believe. In this
But
case, in this
I
one
think
where
you're
there's
asking
a
about
reflected version.
Yeah.
how much the tile is rotated,
Yeah.
not whether the tile
Thank
is
you.
not, right?
Well, we need both.
I mean, we need both. Agreed.
They both matter, right? They both affect
Right. But if you
how the
know
lines.
both the rotation and the reflection of every tile, right, and the ratios between those, then you can calculate the parallelity map directly from that, right?
But in the
You can't
limit,
go
but in
the
the limit,
other
the
way.
Not
perimeter
quite.
Or
Wait. This
you can't
is
go the other
hypothetically
way.
zero
You can go the
compared to the
one way.
inside of the set, right?
This is a tiny detail that I haven't mentioned yet, but the way that I was carving these line segments, I wasn't differentiating. I was just carving all of them, and I wasn't differentiating between one that is like a
Yeah,
border edge
as the
and one
shape
that's a
gets
shared
bigger,
edge.
right? As the shape gets
So
bigger, the
let
perimeter
me go to a
is
super.
vanishingly small compared to the area on the inside. Yeah.
That doesn't tell you what it does at finite times, but it still answers what it does at infinite times for that reason.
Oh, interesting. You're saying that in the infinite case, it doesn't matter what the perimeter is. Effectively falls away.
I think.
Is that
Yeah,
true though with
right.
the edge also getting infinitely longer? The edge itself, it gets, more and more rough and quote unquote longer as the tiling gets longer. Um is there any way of knowing like
Maybe
if it
based on the
grows
dimension,
slower or
like if it
faster
has
or something,
dimension
right?
less than 2.
The side lengths are all one.
Mhm.
I don't know what the dimension is. But
Well,
the thing that I was going to clarify is that I am in the cases of these parallelity maps, all the ones that I've found, I'm counting shared edges the same as perimeter edges,
Mhm.
and it
Right.
does matter because sometimes on like um, other Lindenmeyer systems, like the Levy C curve, for example, that one self overlaps sometimes. And so you could count all overlapped lines separately, or you could treat them like the same line. And I was just having an assumption of like the minimum number of lines that it would take to represent a certain iteration of the Lindenmeyer system. So I can't remember exactly where I was here, but yes. Oh, other interesting things to maybe consider for parallelity maps. The one that's really gotten stuck in my craw that isn't aperiodic monotile related is just what does the sequence of parallelity maps of n connected points on a circle look like? I started working on the first dozen iterations of that, and then it got very complicated very quickly. All of the gray cuber representations of cyclotomic polynomials, those are just sets of points on a circle, and so you could just connect all points to one another, like to the adjacent point on the circle, and then find the parallelity map of that shape, and I wouldn't even know what to speculate as an interesting possibility there, but I couldn't help but speculate. This this is another example of a space filling curve, just a beautiful Lindenmeyer system, and I haven't checked any iterations here. I don't know if it does approaches a constant ratio or oscillates or something. Um, Actually, if you consider endpoints on a circle that are just evenly spaced, but not like all the way connected, just connected to adjacent, n-gons, the sequence of n-gons essentially. Um, the parallelity map kind of oscillates at each layer because if there's an even number of sides, then there's two parallel segments in each orientation. But if there's an odd number of sides, then there's only one. So for the sequence of n-gons, you have parallelity maps that have like lengths of 2, then lengths of 1, then lengths of 2, and then the number of actual orientations is like double and then n, and then double n, and then n, and so on and so on. All tilings, right, are just sets of polygons. The toothpick sequence, that was another one that I wanted to. We love the OEIS here. Here's another sequence, right? And this one, I
Oh.
believe,
So
does
if you
not
only track
approach a
like the
constant ratio. It does
sorry,
not
go ahead.
converge because there's always some n that's like infinitely far out where only 4 line segments are added, and so at some n you have like a tremendous number of vertical segments added, and then 4 horizontal segments, and then a tremendous number of vertical segments.
Does that compare?
So I don't actually know if this one converges or
How
not.
does that
Maybe
compare
yeah.
to the number of existing line segments?
Sorry, say that
I
again.
think what he might be saying is that for the same reason as before, like the amount
Yeah.
that is being added at any given
Well,
time
the
is
number of
is
existing line
like
segments is just growing,
diminishingly
right?
small
It's just
compared to
getting
the
bigger.
area
But
of
then you can see
existing
just a moment
toothpicks.
ago there was like a
Correct me if I'm
moment where
wrong, but
only a
I think
few,
that's where you're leading with that.
exactly 4 actually, one at each corner segments were added, and then after that, more of the vertical or other orientation were added. So um,
What is that frayed carpet one?
Yeah.
That looks so cool.
yes, yeah, it would be shrinking, but okay, yeah, maybe it does converge then. I would assume if it does converge, it converges to like a ratio of 1 to 1, same amount of horizontal and vertical, but that's just an assumption. I don't actually know.
Yeah.
So
Yeah.
yeah, I think. Oh, I should go to the fractal curves. Um, this was a cool website that I found. Some mathematician author wrote it, and I feel bad for not having remembered his name before I pulled up his website. But there are just a lot of well-known sequences of generating curves and whatever of Lindenmayer systems. And I mean, there exists some parallelity map for all iterations of them. Um, and presumably for some there is a limit that the ratio approaches, and in others there is no limit. I don't know. I haven't dug into all of these. Again, this is a kind of a
Mhm.
project that if I'm just running around counting by hand, it's really difficult to try to suss these things out. But for people who might be competent at wielding Python or whatever, uh, these answers start becoming
I'm
a lot
curious about
more
your thoughts on
in
the
reach
cyclotomic,
and
because that's not
accessible.
like a limit. So is the question just about like making a limit from that, or just the discrete?
Uh, so you can my understanding, which is limited, is that you can have
Yeah.
any number, any natural number sub 5, right? You can represent any the point is you as that n increases there are more and more
Mhm.
representations, and these are all representations for the same number here, for the same cyclotomic polynomial. And I would wonder, do all
Okay.
representations for the same number have something in common
So
on
you
their parallelity
compare of
map?
all the same number, and then as we
Right,
increase that number, there
or
will be
uh
more and more
yeah, like
different. Mm, yeah.
correct. And you could even take the average of all of the same number, right? You could take this and try to find an average if there is one. And yeah, I couldn't speculate very interestingly on that, but someone surely could.
Mhm.
One of the things that I was working on was finding the formula for the Sierpinski rug. That's a really well known uh, L system, and I realized that the Sierpinski rug is basically just a square for 9 squares tiling, right? Where at every iteration the middle square is just removed. Um, Everyone can picture that, right? I should have added some nice visuals for this one, but essentially I was trying to find the equation, and it was extremely not obvious. It was very hard to find until I started trying to like find a sequence of numbers that was the difference between the Sierpinski rug and then a square for 9 squares. And I did manage to find
Right, as you're
a
tracing
kind of
paths,
complicated
yeah.
formula that does give the number of vertical and horizontal edges for all iterations of the Sierpinski rug, and that
I'm
was an
also thinking
exciting
though, like
moment.
as you have like paths, like
And it made me realize
ones, like
that
there's a
that
directionality to
space
the
of
direction that your
parallelity
pen
maps
is moving,
is,
Like for example, in
because
like
it's
that
half
frayed
of the
carpet
plane,
there.
there's another
Um,
half available there, and the idea
right.
of like a negative orientation kind of makes sense if you're adding two parallelity maps together. There is such a thing as a negative parallelity map, right? And it's just like literally the other side of the line. Um, so I exactly. Uh-huh, exactly. There's always an orientation. Um, so, although, if you were just saying that, like, let me think about this for
Right,
a
right,
sec.
right.
If you're trying to say that that you could have like a positive horizontal or a negative horizontal motion. That's not what I'm talking about. I'm talking about like the difference between here's one construction and then here's another construction. The difference between these two is 2 horizontals and 1 vertical. And so you would go to a parallelity map here, and you would go 2 horizontals in the negative and 1 vertical. And then that's like a number. You can think about each parallelity map as kind of like a value, a single value in and of itself that could be added to other values. And it's
You're
kind of a
saying
vector space in that sense.
I think so.
So negative
Yeah.
parallelity maps, those exist, and because
Right.
because of the way that the plane is being divided here, because you're including this horizontal but not this horizontal,
Yeah, that makes
you
sense.
can kind of just imagine stitching this side of the line to this open side of the line here and making a cone out of that half of the plane, right?
Yeah.
Is that an easy visual? Like the idea of making the idea of making a cone from half of a plane, from like using the origin as the vertex, and then 1 and -1 get joined together as the same point on the cone, and so on and so on. Right. So, anyways, because of that fact, parallelity maps exist on this cool conic surface, and if you imagine a sequence of parallelity maps,
Question.
you could very sensibly map that in that conic space. You could make some way of representing, a 3D object that touches the cone at each one of those points in the sequence. And for really boring parallelity maps, that's kind of a boring prospect, right? Like here, you just have like 2 points on opposite sides of the cone that are always the same distance from the origin. That's not a very like interesting 3D thing. But for something really chaotic and weird like the aperiodic monotile, the sequence of points that you get on this conic surface are very kind of scattershot. And if you imagine trying to like connect them in the 3D space inside of the cone and make some object that touches at all of those points,
I have a question about
it's very interesting to try to
the
imagine
parallelity
what such
map for like
a
the
conic
snowflake.
object would look like. And again,
Are
I'm
those is it the same map at
go
each
ahead.
level? Like, is the map
Uh-huh.
normalized or is it longer? Does it get longer each time?
Uh So it depends how you want to look at it is the answer. Because again, scaling in a Lindenmeyer system is like a free action almost. You can just do it in the actual rules of the Lindenmeyer system. So there is a Lindenmeyer system that takes a unit triangle and then creates the Koch snowflake that's smaller and smaller each time. And the scaling rule in the Lindenmeyer system could be something like make all of the segments sum to 3 or whatever, right? So as the number of segments increases, the total area gets smaller. Or you could have the total area that they bound stay the exact same, but the length of the line goes to infinity as the iterations goes to infinity. So scaling, asking like, is it the same size for all iterations? Well, is the snowflake itself the same size? Right here, the image that I picked has them kind of like shrinking down a little bit, but the table that I've made assumes that all segments, all continuous segments, are unit length. Right. That way I can just
Depends how you
Mhm.
define it.
um,
Yeah.
and yeah, that question of like, is it the same size? It's definitely the same ratio, right? It's definitely 3 orientations that are evenly spaced from one another and are the same. It's a constant ratio at all iterations. But like,
Yes.
does the snowflake
Kinetic
get
system.
Yeah.
bigger? Does the map get
Depends on how
bigger?
you want it.
These are
Yeah.
questions that are kind of uh, unimportant isn't the right word, but like trivial based on how the Lindenmeyer systems work. Because that scaling can be baked right into
Yeah.
the rule of the system. Does that answer your
I have a
question?
question about
Go ahead.
I kind of got lost around negative line segments. Are those just lines being used to cancel other lines, or are we actually talking
Yes.
about? Okay.
Yes, they're there is no such thing as a negative line segment, but as far as like the operation of adding two parallelity maps together, a negative line is the difference between them, right? It's what's added to cancel out.
Right. Okay. I just wanted to make sure I was understanding that correctly.
Right. Yeah. So for example, if I imagine a parallelity map with like a tau over 6 orientation, but it's of -1 length, and then I add that 1 unit of length to this parallelity map, then all of these have the same length, or 2, sorry. But yeah, it is just a canceling value, and you never see a negative line.
Okay.
Wish I could show you guys the drawing that I did of the how I got the Sierpinski rug
talking about, like,
formula, because in trying to figure it out, I kind of had to come up with a Lindenmayer system for the fractal that is the difference between just a regular grid of squares and the Sierpinski rug, and that difference, that fractal that is the difference in lines, is just kind of a neat
It's like a bunch of
fractal
But like the
tic-tac-toe
center
grids.
one
consider
wouldn't
on
be a
its own,
tic-tac-toe
but
grid, right? It would be like
I
a
did
9 by
not
9 or
Does it look like a bunch
27
of
by 27
tic-tac-toe
generate it
tic-tac-toe
on a
grid, right?
computer, so I can't share it with you guys.
Okay.
Okay. Option.
Sorry, say that again. Yes, it exactly
Right.
does. It's
Yeah,
literally a bunch
yeah,
of
yeah, yeah.
tic-tac-toe grids, and they're bounded in a different color line that I needed to use to make the rules work. But yeah, it is exactly a bunch of tic-tac-toe grids.
Yeah, what if you're done? I
Correct.
have a
Yep,
lot of
it would be a big
questions.
giant one.
Okay.
And actually, all the ones around it, depending on what iteration you're at, they will be, correspondingly of some size that's determined exponentially. So there you go. That's parallelity maps. Any other questions? Any other ideas? Does someone have a cool sequence that they want to show me that's like, oh, check out this one?
I was so at the end of your slides. I was holding some things back for question and comment time.
Oh yeah, that is the end of my slide. We're officially in the discussion.
Wait.
Okay,
Can you elaborate? I want to hear
So one
what
thing
the
that
relationship is.
it came up kind of in the chat and connects to actually multiple different things in your talk. Do you know anything about projective space or projective geometry or anything like that?
Almost nothing. In fact, I'm going to say effectively nothing.
Okay. Yeah, you may want to look into that after this. Yeah.
Brilliant. Yeah,
So there's two different things that connect. One is, so the initial idea when you were presenting like parallelity map, and we have angles, but we only have half of them, and so it's kind of like you're kind of taking a circle, but you're half of a circle. You're kind of identify, and you have the tau, but you have that dotted line because you don't have the other side. And so
Right.
like the outer kind of part of this is kind of like you're taking a circle, but because these represent whole lines, you're identifying points on opposite ends of the circle. Right? Yeah.
Correct.
So like there's 1 point for horizontalness, not 2, etc.
Yes.
So
Yes.
the thing that you get when you identify opposite points of like an n-dimensional circle is projective n-dimensional space. So the outside here, like ignoring the, that sort of half of a circle that you're suggesting for these lines, is what is known as the projective line, for instance.
Okay.
And that's just a name for the idea
It
that
is
like
the
you had the same
projective
idea, but then you're adding onto it by giving, sort of numbers for various points on it that say how much the length of the fractal or whatever is. And then the other thing,
I'm adding this to my list of things to go self-study later, because I didn't mention this at any point, but as I started digging into this, and as I started trying to answer like the initial question of what's the deal with this particular sequence, I kept assuming at every single moment of questions, like, oh, someone's definitely already done all this before, and and I'm gonna stumble into some like well-known area of mathematics, but I literally could not find almost anything. I worked way harder than I needed to get to all of this, because I couldn't find anything that was that seemed really related. And so projective space is a great thing. I'm sure there's some good YouTube videos out there for me on that.
And then the other connection to the stuff that you were doing is at the very end, that discussion you were having with the Gray Cuber about, like, do we have these scaled code curves or not, or whatever? Because what you're really interested in is kind of just like the ratios. You don't really care if it's, 16, 16, 16. I don't remember the numbers on the code curve slide.
Yeah.
And so,
Yep.
in some sense, you only care about that sequence of numbers up to multiples. And when you
Correct.
care about non-zero vectors up to multiples, that's also projective space.
Okay. So this is a double projective space.
This is just like
concept.
2 different points in your talk that happen to connect to the idea of projective space. One is just the projective line, which represents all the directions that lines can have. And then the other is, if all you care about is ratios, it's kind of like you're looking for, the point in projective space that represents the ratios in the limit or whatever.
Yeah. Okay. Interesting. So
Anybody else
yeah,
have any
it sounds like
questions? 'Cause
parallelity maps
if not, I wanna
just are a
pick your brain
projective
about
space, like
just
a
aperiodic
combined
supertiles,
projective space or something.
Something like
abstracted
that.
from the problem. Go for it.
Interesting. Okay, I'll do some research on that. That was the other thing that I don't know if I said was I'm very excited to hear the stuff that you guys know better than me that will that will let me find something useful to go study about this.
I do have something I would like to chime in on. So I have worked on
You're saying
similar problems like
are you
this
saying like transform the parallelity map
in
the
my
same
time
way
on
that the L
puzzling
system
Stack
tells you
Exchange?
to
I have
transform
seen
the
people
whole shape
discuss
as a
like
whole?
the ratios
see.
of split tiles and using the inflation rules to do that. I think I alluded to this in the chat earlier, but I was thinking you can use the inflation rules to like combine translated copies of the parallelity maps with themselves. How the act- Exactly. And I think that allows
Oh yeah, by just fiat rule of saying like and at each step scale so that all segments add to 1 or something, like is that what you mean?
so bring up the Coke Snowflake one again, just so I can talk by example here.
The Coke Snowflake, yep.
All right. So there you have the L system where the one segment becomes 4 segments, right?
Yes.
So you have
And I should clarify what that's saying there is that you start with like a unit triangle, and then at this stage, all of these line segments are still unit line segments. The drawing here is not to scale, but the table here is assuming that you start with a unit triangle, and then the next one is like unit, 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 etc.
yeah. But it's fundamentally it's a map on the individual segments. So let's just look at the top segment for a second. You can describe that system by saying that one horizontal segment becomes 2 horizontal segments, a segment rotated by tau over 3, and a segment rotated by 2 tau over 3.
Yes.
Which means that the map for Gen 1 is 2 maps of Gen 0, one map of Gen 0 rotated by tau 3,
Will it cause
and
any
one map of Gen
problems
0
for the
rotated by 2 tau over
tiling
3.
that
That's what
each
I'm
time
talking
you
about.
You are
overlap?
exactly
And
correct.
so, like, the inner
Yeah, there are negative line considerations. That is true.
It-
You can't quite apply it directly, but
is the amount that overlap easy to
Correction.
calculate?
For overlapping.
I mean-
For the example of something that overlaps, this fractal curve literally has line segments that are like self-overlapping, that are just mirror copies of themselves. Oh, this one right here. This segment down at the very bottom.
Right,
It's a
right.
terribly zoomed photo. This segment literally overlaps itself, and so you could right here at this particular end of the rule iteration, you could either have a parallelity map for the minimal number of line segments that it takes, the ones that you're looking at right here, or you could have a parallelity map that describes, that has an extra count for those segments that overlap. It's the same way that on a tiling, for example, you could have a parallelity map that describes all interior segments as two segments, right? As separate edges of tiles that need to be counted separately. Or you could have the parallelity map that assumes the minimal count and treats all edges like one edge.
Right.
Right? So that's kind of just a
Yeah.
choice that could be made.
Yeah, and depending on
And it is actually interesting. Sorry, go ahead.
yeah, so depending on how you choose to approach it, there are different methods
But-
you may have to use to account for that. I'm sure
Correct.
in most cases, like the proportions of overlap generally will tend to 0. But depending on the system you use,
Sometimes.
yeah, as I say that, I realize that that's
Right,
just
exactly.
completely
Well-
wrong. But
Yeah, tiling is going to have a lot of
Well,
overlap all the time.
Tiling is a perfect example of having a lot of overlap all the time. This curve right
But
here
it's
doesn't actually overlap at any point. It has some like corners, some intersections that are just points, but it is self-avoiding. And tilings are not self-avoiding inherently because of the shared edges. So my assumption was the whole way through just like only count all edges as you only use the minimal representation needed as the thing that I'm counting for. But you could imagine calculating for the Levy-C curve. There's some sequence of parallelity maps that is like the minimal sequence, and then there's another sequence that is the true sequence.
Well, so I was just gonna say, like,
there's some difference
um,
between those.
I don't know.
two
Maybe I don't know
sequences,
exactly how
some,
the system is
there's
defined
more
in terms of
in the case where
like
you're
the L
counting
system,
all of
like
them,
how it's actually written for
separately, but
the
then
case
there's
of the
fewer in the case where you're
aperiodic
counting the minimal
monotile.
amount,
But like
obviously.
it
And
from what
so there's an
axiomatic
example
system
of
said, like that
how a
may or may
negative
not just be
parallelity
the
map
answer to your question.
would make sense because it
like
would
in
be
terms of
the
if you
difference
just
between
like
the maximal
adopt
and minimal count,
the rules
right?
of the
It's
L system
the
to the
thing that you would
the-
add to one to get the other.
I forgot the name for what you called it.
Right.
I think
The
TwoSwap
map,
has something to say.
the parallelity map. Like I don't know how easy the rules are to adopt, and if they are just naively copyable into that context. But like I think you can just make like something like a Markov chain to solve at least the infinite case when there's no there's always precisely two segments touching any point in space. Like oh
Parallelity map, yep. Got it. I want to find
Yeah, I am.
the system
I
written out
linked
because it
the-
is so vastly out of my league so far. Even if that is possible, I am not the person who could do it. It is a complicated
So
system.
I think there's a confusion between two separate things here. So a lot of people have been talking about L systems and emphasizing L systems, but L systems are more specific than like the way the tiles are generated on that link you were showing us at the very beginning. The way the tilings are generated on that link at the very beginning, that you see on the left, it says category H8, and you can just see. And so go back down to, I guess, do your 1-1 tile and like reset it and build super tiles once. Yeah, because H8 is what you.
So here's H8. Yep.
And so
So this is the one
Yeah.
that I was using.
And so the thing you just did with H8 go back to H8. Like,
Uh-huh.
the rule is turn one tile into this thing you just showed. There's separately a very complicated
Correct.
thing which obeys the rule, like, which is technically an L system that we don't have to worry about, because this rule of turn one tile into the thing we're looking at right now is far simpler than that technically an L system thing that I'm not worried about. And to swap.
True, but that rule of turn that one tile, start here, and then turn it into this, you need the full context of the L system in order to be able to do that, because it's not just that at every that here we're going to take the 1, 2, 3, 4, the 8 tiles here, and then replace each one of them literally how we replaced this starting one for these 8 tiles, right? It's not just a 1 tile for 8 tiles swap that's happening. The L system is more complicated than that, and I think you need the full context of it to say, like, okay, this point right here is defined by some point on this other fractal. This fractal right here of super tiles has some shared point with
What
the
is the
tiling that it
definition of an L
corresponds to,
system?
right? Actually,
Is it
let's not show
specifically
that.
a string rewriting system, or
the
is there
Lindenmayer
some
system is applying to the super tiles here. And as this iterates, these are periodic in a way, and this tiling of super tiles is the L system is a lot simpler. And then there's like
repetitive
an
like
ancillary
algorithms that
step to
copy
the
and
L
paste
system,
things?
another
Okay,
layer
yeah.
added on that says, by these rules, convert this super tile, this set of super tiles, into this set of hats, right?
Okay.
Oh, here's the real truth of the matter. It might be specifically only systems that can be rewritten as alphabet strings, and maybe, but when I'm using that word, I'm referring generally to like a rule, an axiom, and an
Yeah, sorry.
yeah. It's a rule that is iterated, a starting point to iterate from, like an initial axiom, and then some unit that is constant across iterations. So in this case, the unit is an aperiodic monotile, right?
Yeah. Yeah, so yes, the things we're looking at now are not technically L systems, but there is like a workaround that I linked earlier that like
Wait.
is an L
Sorry,
system
hold
to
on.
generate
Say that again.
tilings.
If you're taking the
And
cluster
Sawdust, you're
Correct.
and
absolutely
replacing it,
right that it is
like-
not as simple as just replace each one tile with that cluster that we saw on the H8 screen. But it's almost that way because
Okay.
go back to the thing with H7 and H8 because these other is
Uh-huh.
like so those two gray ones is like a cluster of 2, and so the rule, like when you have that cluster, you replace it with this H7. And so if you do both of those, like keep those clustered together and apply the H7 rule.
Mhm.
Okay, so
He's correct. Yes. Go ahead.
so there are 2 rules to like make bigger
Okay.
tiles for the dresser. And so if we go back to like H8 and the single tile, like reset on H8. So like one rule, and then we do build super tiles once on H8.
Clusters
so one
turn
rule
it into the
is if you
H7.
have a single tile, replace it with
What is it?
this these 8.
Oh.
But then you see the colored pair.
You're saying each
so that colored
individual
pair,
element of the
I don't know if it's,
that like
yeah,
but
it's
between
like-
the two of
like a
those
flip.
colored ones,
There's a
each
flip
of them
involved,
turns into one
and so
instance
that
of
pair,
H7.
let's call a colored pair a cluster.
Or am I missing?
And then there's
Go
a
for it.
separate rule for what clusters do. They do 8-7. So if you go to 8-7,
Yep.
clusters become this.
Hold on just one moment.
Yeah. Yeah. So clusters turn into 8-7s and singles turn into H8s. Axiomatic system seems to be confirming in the chat.
Oh,
No.
so hold on. Can I just jump in here really quickly? My understanding is that H7 and H8 are the names
Can
of
you just hit
two
build super
different
tile like
rule
1 or 2
systems.
times because I
It's
need to like see
essentially
it happen. Okay.
you can imagine two different Lindenmayer systems that have the same starting, the same initial axiom of this exact tile right
Is it
here in
always
this
just a little arm?
orientation. And then there's two different kinds of rules. There's the H8 set of rules and the H7 set of rules.
Is there meaning to
And,
the names H7 and H8? Is that some like group theoretical
maybe
name
I'm
or
dead wrong
something?
about that.
paper
But-
says
oh,
otherwise.
sorry. Now I am
Okay.
understanding what you're saying. So yes, this is
Is it
the
known that those are the
H7
only
is a
two
rule that is centered around the
categories
clusters,
of
and then
tilings?
the H8 rule is a rule that is centered around the individual
Right.
tiles. Yeah, and here's you can see that the difference between H8 and H7 is just this little arm that is even or not. It's proportionally little. It stays.
There's 7 hats and 8 hats.
So I'm pretty sure that there are 9 total rules, but that effectively only 2 of them are different or something. That 1 through 6 and
Mhm.
8 and 9 are like all exactly the same, and then
I see.
H7 actually makes
I climb
something
in for a
different
second?
for whatever reason. Like yeah.
Yeah, so H7 and H8 are sort of, they're two different fundamental units of the tiling. There are sort of two parallel L systems, two parallel substitutions happening at the same
Yes.
time.
Wait,
One set of
but I mean,
tiles
if you know the
becomes
orientations
H7,
of the
the other
tiles, you can
becomes
compute
H8,
the orientations of
and
the
that's why
lines,
the
right?
difference is the arm, because it's the image of that extra tile that H8 has that H7 doesn't.
Right, yeah.
That makes sense to me.
Oh, and Two Swaps said,
But yeah,
go ahead.
in short, I am pretty sure that the orientations of the tiles themselves, which is like well known and understood, is not the same as the orientation of the segments between them. Like where those are two different things in some sense. Yeah. I guess yeah. In an infinite case where there is no boundary, yes.
And I just want to.
But the thing is, there kind of always is a boundary. Actually, I just realized this. So, as we said before, scaling is just a free action in a Lindenmayer system. You can just decide to scale something bigger or smaller, and it's just kind of baked into the rules of how you iterate. And so let me go to this to my square for 4 squares example. You could have just a starting square that's divided by 4 and then unscaled, and then all those smaller squares divided by 4 and then unscaled, right? And you could just keep subdividing without making the outer perimeter actually grow at all. The outer perimeter would stay the constant square that it is, and you can do that infinitely many times. And doing that process of subdividing smaller is exactly the same. It's literally identical to this process of growing more and more bigger, but keeping the units the same. You can choose to either have the perimeter remain kind of fixed and then subdivide internally, or you can have the units inside remain fixed and have the perimeter expand around them. And in the same way, with aperiodic monotiles, this boundary, this outer edge, you could kind of just fix it in place and say, okay, it is going to be at these points here. I'm going to put these 5
Well,
arms
no,
on
think of
these
it, think
5
of it this
points,
way.
and it's just going to
The
stay
internal
there.
area
And
of
I'm
the
going
shape is
to
always
infinitely
going to
iterate
be
inwards,
like
smaller, essentially. And in that
increasing
case, you
quadratically.
have an
Maybe a better
infinitely
way of thinking
growing
about it is
set
the amount of
line
tiles which
segments that are
touch
getting
the edge
shorter, right?
is
Those inner
always
ones
going to
are getting
be
smaller and smaller each time.
increasing linearly
And
as a
your
function of the size of
perimeter
your
is
blob
getting
there.
longer and longer.
Of course, I
It's
don't have a
getting more and
proof
more
because I don't actually
fractally,
know the rules
scaled.
of generation, but it looks like from the button
So
that you've
in
clicked a
some
couple of
sense,
times,
even in
like
the
it looks
infinite
like that
case,
seems to be a
there
hard and
is
fast rule
still
here. That
a
like
perimeter to
the
contend with,
percentage of
because in that
tiles that are
infinite
actually
case,
touching the boundary is just
it's
shrinking.
exactly
It's
the
well, it's
same
increasing
as
linearly, whereas
a bunch of, infinitely
internal
many
the
infinite
amount of total tiles is increasing quadratically, or sorry, exponentially. The length. Well, don't worry about the
Mhm.
length. Like, just think about the total number of tiles, because if you know the number of tiles, you know the number of edges, right? And the ones, I mean, the amount of tiles, the percentage of tiles that is in the interior is shrinking each time you press the button. Sorry, I said that backwards. The amount of the amount of tiles that's in the interior, the percentage of tiles that's in the interior is growing, and necessarily, like if that keeps growing like at a constant rate, you're gonna end up like
But the
having
length of those
the
internal
perimeter
edges is
to
not
internal
increasing
line
quadratically, is
ratio
it? Like the
just
total,
approach zero.
the sum of them, if that makes sense, is I I know that. Okay. Mhm. It's growing, yeah.
Sure, but that's not what we're dealing with. Right. You could do that, but like that's not what this approach is in the infinite
Can you go
case.
back to generation
That
1
is
for a second?
true. Yes. Real quick, I just wanna say, you can imagine that, a Lindenmeyer system that's, like, exactly the same as what we're looking at here, but at each stage, the internal line segments, right? Because again, we're not actually talking about tiles. I'm only thinking about ratios of segment
Right. Mhm.
orientations. So, a modification to this system would be to just delete all of the internal uh, segments and only literally consider the perimeter. And
Not what he said.
okay, sorry. Then go on.
Bring up generation 1 of
I interrupted.
either tiling for a second.
Mhm.
Sorry, one step beyond the single tile. Perfect.
Oh, yep.
Yeah.
One iteration. Yep.
If you imagine that this is the rule, you just take 8 copies and match them together like this. Your area
Right.
is going to go up by a factor of 8, but you have these interior perimeters that are canceling. And in the limit, as you do this, the amount of new perimeter
The
that
area,
you
no, but the area
cancel
is
is going to
the
approach
area is
this
totally
proportion.
relevant. Like even though you're
So
like
the
I
perimeter
understand
is
the
going to
questions about
increase
like
by a
the
factor
amount
of
of line
8,
segments, but like
reduced by that
follows stream from
proportion, which
the
is going
area
to be
of
a
the shape,
smaller
because
factor
like
than the area
the amount of
increases by.
line segments that you can have is bounded by the amount of
And so you're going to have
shapes
that
that
the
are
area
present, right?
outpaces the
So if you know
perimeter
the number of shapes that
in
are
the
present,
limit,
you can figure out the
because
Yes.
proportion gets
up to
divided
maybe
by whatever
like
your
some
resulting
factor
ratio
of
is.
2 or something, depending on like how many of them overlap or
That is
something
that
like
is
that.
absolutely
You
true,
can figure
Jerry.
out
I
how many line
understand that.
segments
But
you're going to
the
have, or at least estimate it
in
very
this
closely, even
particular
in the
case here,
finite
at
case.
this
So,
iteration, the area
yep.
isn't being considered. I'm trying to wrap my head around how like the length of each. Uh-huh.
That's 14. Yeah, that's 14.
Yeah, to say
Uh-huh.
to say what Tucson was saying in a slightly different way, the
14.
the area of everything that's not touching the boundary times how many edges does
single
this
tile?
thing have? Like 10, 12 or something? One?
Yeah.
Okay.
It's 14.
10 and 15.
What?
Give or
There's
take.
one of them. A single tile.
Oh, sorry. For a single tile, it's
14.
all orientations have 2 except the one orientation.
No,
is-
I don't care about orientations yet.
So
But thank you. Okay, so
Okay.
14. Okay, so those 14 line segments, maybe they sort of count half because they're counted for they're on this and they're on a touching tile. So that's 7. So
Yeah,
the
that's
area
correct.
times 7
That's. I don't think that's
is
the
a
point we're trying
lower
to make. Though.
bound
Like
for
we're
how
just
many
saying that
line segments you
at
get
any infinite
from
case,
like
you can
interior things. The
you
interior
don't have to think
area
about the
times
boundary. I
7.
think that's the main
Okay.
point
And
that
so
we're
that's
making
and so
here. Is
what
that,
if this
Go on.
this is not the case, but imagine with me for a second that the tiling of this shape had all of the tiles in the exact same orientation. If that was the case, then you would have one orientation of segments that was twice as long as the rest. If the tiling
Yeah.
always had
So if you
the
just
same
assume that
orientation
the
of tile, then there would always be one orientation that was like particularly longer. Is that correct?
if you assume that the perimeter goes away and
Well,
you find the if there exists the proportion of each like rotation of the tile, then you can just for each
I think
rotation,
I do agree with that.
yeah, just take whichever direction has extra segments for that.
Extrapolate accordingly. Okay, and if the boundary, for whatever reason, again, I don't know this for a fact, but if let's say the boundary had a lot of uh, or edges that were in like a vertical orientation, but then in the middle, just based on the distribution of tile orientations, everything was pretty evenly distributed. In the infinite case, wouldn't there be like fewer? Wouldn't that skew between the of the difference between perimeter and interior edges
Not if area grows faster.
factor in? Like, would that not?
It depends if area grows faster. So, this.
Which it does.
Oh, okay. If you agree or you're sure that it grows faster, then yeah, it doesn't matter what the perimeter does because area grows
Ooh.
faster. So in the limit,
no promises.
good. It's
However-
only in like
Okay,
weird
however-
yeah,
things
that
with
makes
like
sense. I'm convinced.
Well,
like the
first of all,
Mandelbrot set or something, where
I'm
like
looking
the
at this now,
length.
and I think we can. I think we might be able
Yeah,
to even
but if
figure
we
out
don't
the
have a
answer
weird
to your
situation like
question on
that,
call here. Like I'm looking.
area
I'm
grows
looking
faster,
at least in
then
the
the
infinite
edges
case.
from
I'm
the
making a
area
claim
from the
about
bulk
finite case.
inside are all that
but,
matters in the limit.
Like I'm staring at this.
Right. Yes. Okay. Which would be the case here? Then?
At this pattern, and like I think we can describe this in terms of like a linear system.
Is
So
there
I guess
a
my
each
question,
time you have a
if I could
transformation
pose a
of
question,
the number of
have
each
I made this
orientation,
interesting enough for someone to
and
make a
I think we
YouTube
can
video
find
of
like a
it so that I
steady
can
state
see the
as you approach infinity
parallelity
here.
maps of the
Either that
spider
or
being
we
changed?
can show that it doesn't
of this guy?
exist. I suspect. I'm
All right, that's fine. I had
okay. I'm just gonna have to stare at this picture for a little. However, that aside, I also for the video that I'm going to post in a couple of weeks, I made a there's a thing that looks like the dragon curve in it, so I made a thing that renders dragon curves. Probably generalize it very easily to do a lot of things that are very similar, possibly including this. Definitely Coke curves. Ooh. Yeah,
okay. I would
you're
be
saying
very
it's.
interested in that.
Say that
Although
one more
I'm
time.
not
What
gonna
was the
lie,
claim?
you definitely just said some words that did not mean anything to me. So you might have to dumb it down a little bit. But okay. Okay.
Just many horizontal as vertical segments. Okay, okay. Not including up versus down directionally. I think yeah. I think I can.
Uh huh.
Well, I think I can prove it just right off the bat, because like
I have
you end up like just starting from the first
brilliant. I have
iteration.
confirmed
Like
that the
obviously
Dragon
iteration the
curve
claim
does have
iteration one
a
the claim doesn't
constant
hold, but
one-to-one
like
ratio
starting
of
with
vertical
iteration
and
2 when you have
horizontal
like a
segments.
single
So,
right angle, after that you're just copying the whole
that doesn't
shape
need to be useful to you. It's just a fun
and doing
fact.
some kind of rotation or transformation on it. So with any rotation or transformation, you're gonna end up with some
Oh, so for the
even
dragon
like equal
curve,
parity of
in the infinite case, there are just as many horizontal as
two
vertical segments.
directions.
Correct. Yep. Only looking at vertical
Okay,
versus horizontal.
I wanna try and solve this here.
And
so
I guess this method
can
of
someone
generating
like
actually,
I'm just gonna stare
sorry,
at this picture and try and like
go
manually
ahead.
write down like what are all the transformations going on. And anybody else want to like independently try and do this while I'm working on it? Am I being clear enough in what I mean by that? You guys? Okay. Well, anybody else follow and want to try and solve it?
Yep,
Because
exactly.
I don't trust myself enough to. Okay, sweet. Let's we can race. Just kidding. I don't want to race. Okay, well,
Exactly.
I'm gonna
Yes,
give it a shot.
that's the case. It's the
Here, I'll
same
share my
like
screen and just
constant
explain what I'm doing.
sequence. Those two sequences side by side are
if
just
you
the same
want.
sequence. Okay.
Yep.
Not to me, but that doesn't mean that you're not being clear.
It goes on for 7 hours apparently.
Yeah, I will gladly try to contribute to
Give
this.
me 1 sec. I'll share my screen.
And I think I know what you're doing, but I didn't want to do it tonight. And I was like, well, if no one gets to it, maybe I'll do it tomorrow or something. So
He's old.
Oh, brilliant.
let me get onto
I stop
desktop
sharing
so
my
I can
screen?
actually do work, because I'm not doing this on a phone.
How am I gonna?
All right, I'm gonna stop streaming right now. I'm gonna try to stay in the chat. See if that works. I'm still here,
Switch
right?
over to
Yeah.
sorry. Switch over to what?
And it looks like Craig is still recording. That name is to be believed.
Woohoo, Craig.
Oh wow.
Yeah. Hold on. I'm shucks. Hold on. I need to stop streaming if I'm going to record this. 1 sec. 1 second. Sorry, I'm recording this with OBS at the same time, so it has to be on the right monitor for me to do anything. Can you guys see that?
Click watch on the 2swap stream, and then I think we'll switch over.
I tried to. Sweet. Okay, so between these two,
I may or may not have had to
we're gonna
click
go just
on
iteration
your
by iteration
stream, which
here.
is now loading, but then I'll be able to see it in a second.
So like, here's
Yeah, so this is the image from the paper.
we
from the
have
relevant
iteration.
paper
So
that
here's
has
iteration.
this.
I'll call this iteration 1. Yes, this is iteration 1. Iteration 2. So now so copying from iteration 1 to iteration 2, we have like one instance of it being like mapped 1-to-1. So what's our notation going to be here? Like I guess I'm just gonna say
All good.
like x.
I think you have
we
to
need some kind of like
reshare your
modulo
screen
6 notation for what's going on here.
because your
and I'm
stream
not sure
ended.
exactly what to do yet. I think so. It's like
Okay, now it's loading.
right, but well, I want to write it more generally so that we can just write a transformation rule effectively as though we're writing like a matrix for a linear system. such that we can just solve for the way that the set of 6 things map to each other in the limit. I think I'm just gonna try and write it like this. So like x is going to be equal to x. So this is, we're saying like, I'm writing a steady state formula. So like as we approach infinity, so we're claiming that the set of angles on this one should match the set of angles on this one, which would be the case for 2 consecutive entries in this list at infinity. And so what this x is going to be is this tile right here, which matches the orientation of this tile. So I'm probably actually going to stare at this one instead, like these two,
like
because I think it's
tau
easier to
over
see with the blue things highlighted. So like
fractions
this
of
thing
turns, but
maps perfectly
that's
onto
also a
this
little
thing.
cumbersome.
Rotating the whole thing, I think by exactly 60 degrees. Is that right? By 60 degrees, we get this one.
So
Is that right? Please check me. Plus, so what? How am I going to write this here? Yeah. Okay. So. Oh yeah. Oh. Wait. As a root of unity, are you saying we're going to complex number this? How do you suggest notating this? Okay. Uh, zeta to the yeah, no, I can't write zetas. Zeta to the pi over, what would that be? Pi over 3?
Looks like
Well, sorry, plus
Is
zeta.
it?
This one's zeta,
Mhm.
plus
Okay.
zeta to the pi over 3. Okay, yeah, this is better. Okay, thank you.
You could use like this,
Yeah.
multiply it
looks
by
like
the
60
sixth root of
Yes.
unity.
Yes.
Oh yeah. Sorry.
as long as you're
yes,
consistent with your
yes,
wrong
yes.
answers, it doesn't matter.
So x is equal to
You
x times. I'm just gonna let
Yeah, you
z
should
be
abstract
e
out
to
the
the
rotation
I
into a
pi over
quantity
3.
and then
Is that
multiply it.
sane?
Well, it would be zeta.
Tau over 6, pi over 3.
Of course.
So x equals x plus
Neither
zx.
can I.
So x, this is zx. This one's z squared x.
So 2 swap can't
This
rise
is an
zetas.
x, yeah. This one's also an x.
Well,
So this is
I'm thinking that the tile is some
what's in each side?
variable, and then
Oh shoot.
the rotated version is zeta times the tile.
Oh shoot. I see now. So this is oops.
Yeah, so
Okay, this is
Yeah.
correct.
This is x. Just to mark my tracks here. This is x. This is
Yeah.
x. This is zx. This is z squared x. This one is y, I guess.
Right.
I think you want pi over 6.
2x.
No.
This
The
one.
middle one is
Oh, yes. Okay.
an x.
Are you sure?
No, that's a Y. That's an H7.
This one's 4th. This one's 5th.
Yeah.
The bit on center right is an H7,
Okay.
not an H8. So you need a second variable for that.
Z to the
That's why I said they
x
interrelate.
Z to the 4th, x z to the 5th. Okay. And then this is y. Okay, so y is equal to
Yeah.
plus x z to the 5th plus x z to the 4th. Sorry about my inconsistent pen thickness. Y is going to be equal to plus y. Right? Y is then the same as
Z to the 5th.
Is this
wait, Z to
does
the
this
4th.
map perfectly onto this thing except with
Yeah, it's
this
Where you
one
want to
is?
represent
Is that what we said
H7
earlier?
with.
4th.
So y equals
No, it's 5th.
all that except
Bottom.
with
Yeah.
No, that's right. Z to the 4th.
Okay, yeah. So y equals.
Then bottom right is no. Bottom is
Can I just? I should just
bottom
be
is
able to
fourth.
cancel this out, right? Y equals.
Bottom right is fourth.
Equals 2.
I agree with two answers.
Yes.
Is that just saying y equals
Yes.
x? What's not good? Yeah. If we literally just write like plus. Well, in the infinite, yeah. No, but well, since I'm trying to do the steady state, like it should be equals in the infinite case, but like I don't know if we have to. Do we treat that separately for the y? Yeah, like I'm thinking like this is like
So with all
Yes.
that,
y
Yes.
equals.
The only
Doesn't this
difference.
come out to be y equals 6x over or 7x over 8? Because like we're just like if this is
Yeah. The thing above except x instead of 2x.
if this is 8x equals this thing, then you like subtract 1x from each side. I half believe it, but I'm not entirely convinced yet.
Yeah, the x on the left
let's
side
see
and
what,
right
let's see what
side are
happens.
not the same
So
thing.
7x over 8, right?
So
like
if we wrote
x
the thing
sub-
above
is that
and
what
X
we're
sub
going with?
got
2
rid of
is
an x, there's like x minus
No
x,
one's saying
right?
yes.
Which is 0. Yeah.
Yeah,
If
that
this,
should be an
yeah, if this
arrow,
whole thing
not
is
an
x,
equal
factor.
sign.
and if this thing is
Per
x,
se.
what did I say? 8x.
Oh yeah.
If y equals y can't be equal to 8x, right? 8x shouldn't it be like 8x minus? It's like x minus x. Oh, 8x. Oh, 8x equals that thing.
Oh, yeah. Something like that sounds
And
believable.
y equals 7x. Yeah, y equals 7x. X times 7. Okay, yeah. So in this, okay, yes, that sounds sensible. Plus 7x.
Yeah, I believe
Okay,
it.
cancel out.
Oh
7,
yeah. That works out.
cancel
That works out a lot better.
X equals. I'm gonna rewrite this. X equals
Wait.
2x.
Well, let's see
It's
if we get an
So
answer,
x
and then let's
8x
see if that sounds good.
X
minus
plus x z to the 5th plus x z to the 4th.
Wait.
This becomes 0.
No.
It's like-
Becomes x.
Well.
So x plus zx plus z squared x plus. Is there a
you had a
complex
scaling
valued
before. You
solution
said
to this?
8x, right? Where did the 8 go?
Plus zx plus z squared x. I don't think we're getting off track.
No, I meant on the upper line. You had 8, and then you crossed it out, I think. Yeah.
Right.
And so if 8x equals that thing, then y equals 7x.
Right? Question mark? Right. These are conjugates. Right. These two are conjugates, and these are. These two don't sum to 0 strictly.
Boy, that's right now.
Z and z to the. Oh yeah, correct. Okay, yes. Sorry, I wrote the wrong arrows. Z x and z to the 4th x sum to 0. Z to the 5th and z to the 2nd. Yeah, so then x is just 0, and that's unhelpful. Right.
well, I mean,
Factors
if you were looking for a solution, you
into
would add
z
the
plus z
complex numbers
squared
together, but I
times
feel like that
1
shouldn't be
plus z
allowed.
Is this
cubed, but I
complex
think
number
we're getting
approach?
off
Does
track
this
here.
not work the way that we thought?
Otherwise, we would just get x, because like zx is the negative of z to the 4th x, and z squared x is the negative. So you just get 0 equals x, and that doesn't make any sense.
Right. So like
Z and z to the fourth sum to 0. That'd be the same as saying like having a tile and a rotated tile means that they're both
So-
destroyed. The z is just, we should be allowed to multiply the z's but not add them.
I don't.
right.
Yeah, I don't
Right.
think that's the right way to think about this.
Right. If I attempt to write that out, is this really gonna be as horrible as we think it's going to be? Like, if we have some vector
I was
v,
thinking of like if you have
I think we're losing sight of
if
the
you have
fact
z
that
to
this
the
is
x,
supposed to
and then it
represent
gets
I sure hope you're not
function
asking
on
me.
parallelity
rotate
maps
by z,
that are
then you
all
end up
getting
with z
added
squared.
the
together.
matrix,
so
the
it does a
matrix
good
that,
job
that
of
we're concerned
tracking
with,
that
that
z to
like
Or
the
just
z
counts the
matrix
blind
here
segments
is just
is
a
1.
matrix that
So we
like-
don't
But
want
we
them canceling
shouldn't
negative.
it's like a
add
matrix
them.
there's like a bunch of
Yes.
ones like this, and then like one in the bottom corner.
Yeah.
And then so like we end up with the same
So they're
equation as we
numbers
just
with
said,
an
right?
multiplication
Right.
operation,
But we
not
don't
addition.
want z canceling z fourth
Equals
because those are two lines in the same
two
direction that
v,
get counted
right?
double, not 0 times.
2v
Yes.
plus
Yeah.
the what matrix? I don't know what that means. A what matrix? I can't
Well, I
even
mean,
hear
this
what
whole
word you're saying.
notation
Circulant?
is trying
I don't know
to
what that
get
is. What is a
around
circulant
the like
matrix?
6x6 matrices that 2swap didn't want to start by writing. And matrices are a thing that where their multiplication is special and
Or general
different
what?
than their addition or whatever.
You cut out. I lost you.
Oh wait, it. Hmm.
All good, no worries. This is I circulant.
Yeah. Yeah.
In the meantime, this is I, this is I, this is I, this is Z, this is Z.
You're saying we end up with a circulant matrix? Yeah, that sounds right. Circulant matrix.
Yeah, do a rotation on your elements, yeah. Z to the fifth,
Yes.
Z to the fourth.
Yeah, circulant.
It's basically like that matrix you just
It's-
drew.
And this one
but
is
for a general-
Y. Okay, Z to the fifth V plus Z to the fourth V
Yeah, so
plus
so
All
what
the
you were saying at the
big
very
copies of that.
beginning.
I miss Z squared V.
Oh, axiomatic system.
Okay,
Your
and
audio
why-
had cut out for most of what you just said.
Oh, sorry.
Y ends up being this whole thing except
I'll
for
just drop one in chat.
one of these V's.
You should be able to get the idea.
So
Oh. I'll drop it for anyone who doesn't feel like clicking that link.
right, exactly. Yeah, it's just this whole thing. I'm just gonna toss this Y and then say all of this thing times 2. Right? Why not?
Yeah, so your Z's are like push
Why not?
things down
Maybe
by
I'm not understanding.
one or whatever.
Right. Why would he be misled? Yeah. Yeah.
It follows the same that kind of recurrence, except instead of v equals 2v plus that, it's y
Right,
equals
but
v plus
x
that.
equals x plus x. Like
That cancellation we were doing earlier was
I'm
not the
not
right
following how
idea.
that's a faithful example. Like, isn't it just the same as saying x equals x plus x? Like, okay.
No.
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 Becomes two copies of
Axiomatic
x.
system was just explaining why you should not do that. Because y satisfies a recurrence that looks the same.
Suggesting that
but
we
that
need a
doesn't mean
scaling
that
factor?
y,
Is that
the v, if you
maybe
used
that's not
v in the
directly
y
what you're
equation,
saying,
you
but
would be misled.
do you,
Let's look at a simple example. So the function x becomes 2x, right?
okay,
That
yeah,
tells you the
I
powers
can
of
see
2.
how that is true in the general case.
You can deconstruct that into x becomes x and x becomes x, but those are linear quantities. That's not going to add or multiply or in any sense combine to the solution to the original recurrence. You can't add recursive formulas like that.
On a separate v, are you saying to split out the v into two different v's? Is that the idea?
Well, it's exactly the kind of thing.
Right.
An x becomes two copies of x.
Yes, I agree.
Instead of explaining this,
No.
I thought of an entirely different way that we could
I'm
probably
trying
solve
to
this,
say that
which is
like
just
a difference
directly computing
between
the
two
amount of
formulas doesn't correspond to a difference between the terms that they generate.
No, maybe it's not. Maybe it's probably just the same thing under the hood, honestly. Actually, never mind. Y equals v plus.
Good night.
I was gonna say just write the equation in the chat or something.
Yeah, I'll try and do that.
So like the equation that 2swap has written is the thing I just put fixing the braces. Bother me. And then similarly, we have a different equation with y that's a recurrence where
V and y evolve in parallel. So the v and y of the next generation depend on v and y of the current generation.
Is there any reason why we can't just solve this as a system, like as a system of two equations? I think that, yeah.
I just realized that the conversation you're having about trying to like track two different things in parallel, but not, like adding them together, but their terms adding isn't quite the same as just adding them.
No, I mean,
there was a
solving it
similar
as a
thing,
system given this
and
z that we already
I say
have, this
that with
matrix that we've
a
already
huge
defined.
asterisk. that I encountered when I was trying to find the
Like this is
parallelity
just a
map
linear system now, right?
formula for the
That we can in
Sierpinski
theory
rug.
solve.
And I had to.
Okay.
I
I don't
drew
want to do
out
that by hand.
a system of rules, and I
Yeah,
had
yeah,
to
yeah.
have
I think
several
probably
different
what I didn't
like
realize is that this
operators
Y is
of
also
rules.
recursive, so it's not
There
just
were
a direct like
different
feed in
things
you
that
can
were
just plug in
evolving in
directly.
parallel with one
'Cause you're
another
gonna end
and,
up with the
kind of
same problem
influencing
where you
each
just
other.
plugging a Y right
Um,
into like the equation, and then you
and
just
that
get
feels kind of like
recursive
what you guys are talking
like
about. I don't.
infinity.
What I ended up doing
Uh,
was coming up with a
So yeah,
generating
no, I
function
think I
that
get where you're coming from.
that takes a finite sequence of terms and then like reverses them and adds them with the terms on the other side. Again, I don't really know if that's helpful. I don't expect it to be, but what you're going through right now feels
It's three
very
that-
deja vu-ish.
Well, what answer do you like? The answer we want is like a vector of the amount of lengths in 6 different directions. So if you solve 2 equations like you're doing regular algebra, you'll at best get a complex number, which can only have 2 pieces of information.
Yeah. I think that's the end result that we're working towards, but we got lost along the way.
I
Yeah, because
going back to that, like the counts of the first few iterations, there were like the 3 that didn't equal the other 3 that were slightly larger. I'm now
So
noticing
what
that like
V and
so for example, the third iteration, like 3 of the directions had count roughly 60 and the others had roughly 80. It's like when we rotate by 180 degrees, that doesn't really change the counts of the directions. And since there's only yeah, there's only 6 rotations of the shape.
Yeah.
So there are only 3 meaningful rotations. So there's that one direction that has 2 extra line segments.
That's why
Is that
parallelity
always
maps
only going to
are
be
modulo, half of a rotation.
like
That's just
it
true.
can go horizontally, but can they go vertically? Are there any of these that have that
yes.
extra vertically? I just mean in this picture. Like we have some of them have the extra
I'm
horizontal.
trying to understand your question a little bit better.
Which seems to be
You could
preventing, like if we
start
pick
with
that some of
the
the
very
extras are
first,
horizontal, then
just
we don't
single
get any
N0
vertically.
tile. You could put it in an arbitrary orientation. You could start it
Yeah, exactly.
at,
Perhaps
with the
perhaps
2
the,
extra lines vertical.
Since there's
Right.
17,
I think it's just a matter of solving these
or
2 linear
14,
systems.
which are half to 7.
But I'm not.
4 of them are going
Also, am I
in that
losing my
direction,
mind, or is there any
and then
reason we
3
can't
are going
do
in the
this?
other
Like
3 sets
where
of
we can't just
directions,
cancel out
then
this 2
maybe
and this V, and
the
then just
ratio
call
approaches
Y
4/3.
literally 0. Gotcha. Yeah. Right. Right. I'm gonna call this X.
Feels distinctly possible, I would say.
But
So I feel like we should be, if I'm understanding what people are saying, we should be pretty close Like, okay, so I put Z is this matrix, and
But
then
like, shouldn't this then be X? Can we call this X now?
what?
This is the same variable as
And then so what? V and Y are two
right. So
6
this
vectors.
we're just doing like a skip iteration approach where like this V is no, but this is still
and
V.
Y
I'm
are
calling this
vectors
V
corresponding
X,
to
and
a
this X.
particular generation of H7
Right,
and
that way
H8.
we've
And the inflation map
that
modifies both
accomplishes
of them by the equations that we have.
What does that accomplish? I don't know what that accomplishes. I was thinking that would accomplish it.
Yeah.
A definition of this term
Well, we did, yeah.
as a function of only this term, like without any recursive definition. Wait, so what do we do here?
V's. Those are V's
I'm
at
lost.
two
What is
different
the
stages
next
of
step?
the inflation. Yeah.
That's not supposed. I don't think that's supposed to happen. This is also a like a Y one rank back. If I'm understanding correctly. So this is all just recurrence relations. But I mean the whole point of doing this steady state approach is that you get like some like usually the way this works out is if you like this is how you solve a Markov chain, for example. Like if you have a Markov chain that's just defined with a matrix.
That's what V represented for a brief
where you have
moment.
like V equals
now we're just
some
flipping
matrix
it back
times
to
V.
X.
Like you can just solve for the system to get the steady state of the Markov chain, which is what I was hoping to accomplish here. But I guess the fact, yeah.
What does that accomplish?
Wait, I'm a little
Right.
That would be two applications of the functions that we have.
yeah. Like I have Mathematica open and I put the matrix in, but I don't know what I should do because the y equation on the left looks like the y's just cancel out. Is that supposed to happen?
No, it is not
or am I
supposed to happen.
misunderstanding something?
Yeah. Yeah. X and Y are both. Yeah, these are parallel recursive relations. So
you could just put it in Python and just iterate the system.
yes. Yes.
Yeah, I mean, yeah, it should converge pretty fast, I imagine.
I think on the left-hand side, your Y is the entire state, and the right-hand side, the Y's contribution is only a part of the whole system. So they're not canceling them out has unequal effects on the sides of the equation, so you can't do it just like that. That's the only problem with that approach.
Hold on.
Yeah, on the surface, this is just a simple like eigenvector problem, but I'm trying to remember how you deal with.
I'm going to use different variables to stop confusing ourselves. We'll call the vector of stuff going on here A, like the parallelity map, and this one will be B. Now this one,
and I'm praying the answer doesn't involve just unify them into a single matrix with twice the dimensions.
Because this one will now be. Sorry, say that again.
Yeah, just do it until you stop caring about the numbers. Yeah, that's what sensible enough approach for most people.
Right. Although
In theory, if we just had the
actually,
first,
hold on, the rules.
n thousand
Sorry,
of iterations,
I'm gonna do that instead for
and
this
then just
being
the
A and this
parallelity
being
maps at
B.
each
The
step,
reason for that
we
is
might be able to
because
just
the rule
visually
changes.
confirm that they.
Yeah. I don't know
So,
how to
like,
do that,
the-
but I
the
can
way that
definitely
we
knock
do
out
this
some raw
is-
data for you.
Now,
I wouldn't say no to raw data.
Now, if we write
I have
C
Python
in terms
open
of B,
right now. Let
we
me
have
see if
C
I can
equals B.
bang
We get our
something together.
same big equation again, but we can just subtract off A once.
The
At that
the
point, you get
source
something
code
like equivalent to
for
like the Fibonacci
the
sequence, where you have like
the actual, iterating
Z
the
sub
visuals of each step
like n
is
equals
open
Z
source,
sub
and it's on
n
the
minus 1 plus Z sub n minus 2 or
if you
something like
Google
that.
Waterloo
And
monotile, it's like the
I'm
first option. It's the Craig
hoping,
Kaplan's
then we could like
website
accumulate
about
the
aperiodic
matrices
monotiles.
and then
It's a
just
great resource.
write it out as a whole system. Does that work the way I'm imagining it would?
Okay.
I think you can. I mean, I think
A and R and some.
okay.
Well, B
We'll
can
find
be
out.
expressed in terms of A
I'm
and
ready to
then
find out. I don't know
suitable
about you
syntax
guys, but,
for rotation and reflection. Good idea.
Yeah. So B.
Oh wait, because this
B
neglects the contribution of H7, doesn't
MB.
it?
To be.
Sure.
M to the fifth.
I'm not
B
sure how you solve a
plus B
quadratic
minus
matrix
A.
equation, but that sounds like it would work in theory. I'm absolutely positive you can. I just don't have the foggiest idea how anyone does it.
Sorry, I'm having a brain fart. You can just factor the B out of
I'm
this, right?
I'm
in a
just
matrix
genuinely
equation. There's no reason
thrilled
I
that you
can't
guys
do that,
didn't
right?
walk in here and go like, "Oh yeah, this is just a trivial example of the blah 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 blah."
Yeah,
And here's your answer.
Okay, yeah, I just wanted to make
Read
sure I'm
Wasn't-
not like
wasn't even worth
Kaplan
totally brain fried.
2017
This is 3I.
American Mathematical
3I
Sciences Journal,
plus
page
M plus
473.
M
Bye.
squared plus M to the fourth plus
Right,
M to the
exactly.
fifth
Uh,
minus A times B.
Sawdust, do you have the numbers for like a single tile that slide early
Right.
on? Like, what
Right,
are the
right.
I was just about to ask for
how
that.
many of each direction?
Right. And this is just some matrix.
Wait, say that again. Do I have numbers for
For a single tile,
slider?
like the first, like a single tile, how many horizontals, how many vertical, that parallel
Yeah,
those numbers.
it's two unit segments in each of the 6 orientations, except a sixth of a turn, which has twice as many. It has 4.
Okay.
So-
Great.
Gotta go back.
Yeah,
to the
wait a minute.
stats
So
and
don't we
look at
just
those
find the eigenvector
other
here
recurrences
of
again.
like assuming that A equals B, find the eigenvector of the resulting matrix? Like we now have like if we assume that C equals B equals A, then we find the
Yeah.
find the
Yeah,
find
that
the
was always an option.
eigenvector of like
Yeah. Yeah.
not precisely because I like we're assuming like think of it as like V equals V equals this big thing in parentheses times V minus V, right?
Yeah.
So
The
like
problem only
V
started when people
equals
started
the
saying
big thing in
M2 plus
parentheses
M5
minus.
equals
Oh
0,
wait,
because
maybe that
then
is what
we
you said.
lost what we
Is
were
that what you
doing.
said? Like
Yeah.
okay,
No,
yeah.
but
in
you
that
can
case-
always do this with
yeah, I think we
matrices.
gotcha. Yeah. In that case, I think we just find the eigenvector of this.
Hmm.
Anybody want to do that in Wolfram Alpha or something?
Yeah.
Is M? What? It's different though, right? Why would? Like I'm gonna write out this matrix manually here. Maybe I'll do it in the chat so that somebody can copy paste it or something. Well, no, I'm gonna do it on paper. This is 2,
Yeah.
2, 2, 2, 2, 2. Plus an M. An
Of
instance of
2i
M
plus m
is
plus m squared plus m fourth plus
rotating
m fifth. Yeah.
clockwise. I guess it doesn't really matter my notation, presumably, but we're gonna have to remember to be able to interpret the answer. So I'll say clockwise rotation.
Yeah.
I think it. Yeah, I think it shouldn't.
It may make it simpler if
Yeah, I said
we
2i,
could
not 3i.
replace like m to the fourth with just
I
m
was aware.
and consider
This
those
is
equal
1
since
for
they have
M.
the
This is
same
1, 1, 1, 1,
counts.
1, 1.
Like there's no reason we need to
For
consider
M
them
squared.
differently.
This is another 1, 1, 1, 1.
Believe so.
It's gonna
1, 1. And M to the fourth and M to the fifth is going to be on the same thing backwards.
No. M is a sixth of a
No.
term. M is a sixth of a turn. The different entries in the vector are different by twelfths of a turn, so there's a mismatch there.
Yeah. Yes.
I'm going to look up the eigenvectors of that. Oh,
Yeah,
what are they?
Oh, are you also in Wolfram Alpha or something?
Okay, that's an eigenvector. Gotcha. 1, 1, 1. Okay, yeah. 3. Sorry, 3. Say that again. Okay. Okay.
This might be a stupid question, but does one of those twos need to be a 4 for like the starting tile that we're beginning with, or am I misunderstanding?
With the initial state. This is the evolution rule.
You say there are rotations of that. Which rotations? Does it matter?
Yeah.
Oh, okay, the evolution rule.
Uh,
Got it. Not the starting axiom.
Mhm. Okay.
Yeah.
Wait.
Is this accounting
So,
for that mismatch between the 12th and the 6th?
No, this accounting
this
for the
tell us?
mismatch, I think would give us a 3x3.
Why does it tell us that?
Yeah.
But we're doing it the hard way to make sure
Or
we don't
something.
oversimplify anything. I have
Is that
them
a
up right
thing?
now. 1111111 with eigenvalue 6.
You're going to approach equality of quantity of line segments.
Okay. 3 with eigenvalue 2 that are rotations. 3 eigenvectors with eigenvalue 2. They are rotations of 0,
That's
0, 1, 0, 0, minus 1.
Lots. Sounds like lots.
And 2 with eigenvalue 0 that are rotations of -1, 0, 1,
Gotcha.
-1, 0, 1. Oh yeah, it does because there's only 2 of them. I'll just list them. One is -1, 0, 1, -1, 0, 1. And the other is -1, 1, 0,
Sounds
-1,
like it.
1, 0.
Right, but if all the shapes are an equal orientation, then
So that's everything appearing about
It tells us that
or
1,
equal,
1, 1,
exactly
1,
equal.
1, 1 asymptotically dominates. Because it has the largest eigenvalue, so it
Right.
experiences the largest
right, but
compounding
if you all 6
for each
rotations of the
step.
shape in equal quantity.
Yes, that's what eigenvalues measure. Yes.
Yeah. Also,
Yeah.
yeah, if the recurrences that the Greg Huber wrote in the chat like 20 minutes ago are
But
right, then I
to
independently checked
answer
that,
what we were
like,
saying there, like
you know,
if
30
you
steps down the line,
like
it's
even if
extremely close to
there's
all the same
2
number.
more line
Yeah.
segments going in a certain direction,
It's
like
like,
if all the shapes are
in one direction, it's
uniformly
like, how many
homogeneously
million, billion,
rotated,
trillion?
then those 2 extra line
Like
segments pointing in
they're,
one
they're
way
like
will also
all
be
like
homogeneously rotated along with
32.7 septillion,
the
give or take a
distribution
very
of the
tiny
shapes.
bit.
Yeah. So
Of the
there's an
Right.
equal part
not the line.
that increases by
does that
powers of
mean-
6, and a variance part that increases by
Because the
powers
lines
of 2. So the former
there are
far
6 different
dominates the latter.
orientations of the shape. But like
Yeah,
the
yeah.
100
Does that mean that we have
are they the
officially
same
confirmed
rotations
that
of the
in
lines?
the infinite limit, the 6 orientations appear in equal measure?
Yeah.
What?
But 2 of these shapes are 180-degree rotations. And so the lines will end up
Yes.
the same.
Turning the shape turns all the lines.
Yeah. Also, by the way, that
So like
that result
every
about the
single one of
Rotate a
these
shape,
eigenvalues,
you
like
rotate the
shapes,
lines.
absorbing the steady state
The-
of the system,
Yeah.
like whichever
sum
eigenvalue
of
is highest.
the
Is there a name for that?
triangle pointing upward.
What do I Google to find that? Because that sounds useful.
Correct. That doesn't change the parallelity map. And we have
Is there
we have some number of reflected.
Oh, yep. Yep, you're right. You're right.
Wait,
see
I
that.
took the eigenvalue of the
Is
wrong
most
matrix, didn't I?
Yeah. Oh, cool.
Um,
I did not know. I did not know that that
What I'm
was
saying
a.
is that
I did not know that that
they're
was a known result.
not like there are certain lines. I don't know how to explain this.
Would it be when your starting position is in the in the plane of the of the eigenvectors that are not that main one? Okay. Huh.
This
Could you
feels
zoom
like
in
The
on the
bottom of the
picture?
hat. What's the hat?
that I was
Oh,
trying to figure out with
oh,
like
this. Yeah, I
the
forgot it was called
importance
a hat.
of
Yes,
when I was trying to just
on the big
intuit
one.
this
Okay.
answer, the fact that the outer
Just any
boundary
hat.
is
Are you a magician? Is this going to be a
it's
magic
not
trick?
obvious if just the outer
Let's
boundary
go with this
itself
hat.
has some skew of orientations. Never mind. I don't have anything
On
to
the
add.
left side. Isn't this the bottom? Oh, this line segment, okay. Yeah.
I mean, if you Google largest eigenvalue, then you will find.
So
Like
if
my
you
first hit is
go
the
for it.
Wikipedia page for eigenvalues and eigenvectors. And the largest eigenvalue is of particular importance because it governs,
Yeah, you're right.
and
No,
you
you're
get the steady
totally right.
state. Like that's like the fact that you were throwing around the phrase steady state made me would have made me guess that you. Now the thing is, I
Yeah,
was just
you're
going to
right.
say,
if you
like,
look at the
if you have
bottom
really
of the hat,
unlucky starting
Wait,
positions,
I think you're
the
right. I think you're right.
eigenvector for the
like
largest
pick
eigenvalue is not
the
going to be what you're headed to.
yeah,
But that's why.
like go back to zoomed in on that big one. Yeah,
Like if it's
like
in the.
pick a hat. Yeah, pick a hat. Any
If you have
hat.
a eigenbasis, yeah, exactly.
Okay, so the bottom of the hat, the part that touches your
Yeah,
head on the left side,
right. Well, so but we still have that still
the
gives us the
line
result,
segment.
right? We
Yeah,
still
yeah.
just now have
I'm just
like
trying to
it's
locate one of the line segments. Yep,
there's
the
14
horizontal
original
one.
lines, right?
That
So
never
and
is
like
vertical.
6,
I don't
6,
see
and 4
anywhere
and 4. Is
where
that right?
that's
In
the
each
vertical line.
rotation.
So even accounting for an even
Sorry.
distribution
No,
of the
I'm
rotations,
not saying that right. There's 14
that
and
I was going to say,
line
in
pick a
one like
hat
distance is
out of
orbit,
never
infinitely many
you
hats.
vertical.
have
So each line
how
only
many? You
applies to like
have
3 directions, not all 6.
2, 2, 2, 2, 2, 4, right? So in one orbit you're going to have 2, 2, 4. In the other orbit you're going to have 2, 2, 2. So you should converge to like 6/14ths split evenly across. So like
3 directions that always
uh,
have 4 lines,
2
or
14ths
6 or
split
8,
evenly across
and
3
then
of the options.
3 directions that always
and
have
then
6.
Yeah, that's the.
what would this be? 8/3 14ths
Yes.
split evenly across the
So
other
there's
3
going to be a
options.
4/3.
That's what I was sort of asking. Like, did we account for that properly? Because I was busy doing my own thing.
Yeah. Sorry, that was notational error. Yes, this
If
is
you wanted
supposed
to
to be
pay
a 2.
attention to the lines, yeah.
2 14ths, and yeah, 8/3 14ths.
Oh wait, is that
I concur.
true?
Ignore my use of double fractions in a very bizarre way. 8. I don't want to do the multiplication here. 40 seconds. Yeah. 4.
Yeah. So like the matrix, I see. So those recurrences, the stuff we were doing with like z or zeta or whatever, we really needed
Well,
12 if you were going to do it that way.
Right.
And the z's jump every 2, but the initial distribution is like a weird bunch of them.
there's 4 and then the rest have 2.
Mhm. Right. Yes.
Two, two, two. Yeah.
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 Yes.
Mm,
4/3 is a pretty even
8/14.
ratio, all things considered.
If you're gonna divide one of them by 3, you should. So
But like once
6
again, we're not
40
talking about
seconds
we're not
and
talking about lengths
8
here,
40
right?
seconds. Yeah.
Are we talking about lengths? Or are we talking about
Yeah, either one or both, either both or neither should be have a dividing by 3. Yeah.
so 2? Yeah,
We'll just call
we
it a
started
ratio
with
of
the
ratios.
like
And 8 divided by 3 halves is famously, or wait, no, 8 divided by 3 and then divided by 2 is the 4/3 that everyone had been talking about since the beginning. Right. So thank you, the Great Cuber. So to summarize what we did here, the rotations even out in the infinite limit, but because we're starting with this extra business on 3
sorry,
of the
how did we
directions, the parallelity map becomes the 4/3 ratio that it looked like at the beginning.
how did we
Okay,
arrive
so
at the
wait, that
2
means
2
that
2 2 2 4 distribution?
every
Where did that come from?
other line segment
But
is
like
shorter
Yes.
by.
right, but that's not
Oh my
reflecting
god,
lengths.
that's
That's
fascinating.
just
Okay,
reflecting the
so it
amounts, the
approaches a ratio
quantities
of
of
4
the
to
rotated
3
edges.
per those
On the
longs
unit
and
one,
shorts.
yeah,
Yes,
right.
yes.
On the unit one it is, but that's not necessarily what we're
I'm not
looking
gonna
at
lie,
here, is
that's
it?
probably one of the
It's
least
definitely not what we're
expected
looking at
things.
here.
Does
I would have
the
assumed if it was gonna converge, it was gonna be to like an even ratio. But wait, now this
Okay, gotcha.
does
it's
the,
very
like,
even, to be fair.
relation
It's
hold
it's
for
very
all of the
close to even.
shapes? It's independent of
But
their
now I'm
starting
wondering
lengths?
Okay.
what that means
Right.
for right? Because now this 4/3 is
Yeah,
the
so you're gonna
infinite
you can do the
limit
math of
of
when it
this
cancels out.
So
I guess
center
this
it'd
is
just be
tile on
specifically
that
for the
slider.
unit.
I
And
don't know
so
what it
as
would
we
be.
shift the slider to all the way to the right or all the way to the left, that 4/3 is going to skew
Well, if we pick a different one, then we'll have
something
different
different, right? Like the
starting
parallelity map.
lengths. So that we might not have 4/3.
Well, we are. We calculated lengths.
Yeah.
That's what I understand.
Yeah.
Yeah, you can do H8 and H7
Ex-
regardless of which tile we're looking at. No, it's not specifically for
Correct.
the
Yeah,
unit.
yeah. This ratio. The correct. Yes.
Right, yeah, we won't have 4/3, but we will have the same property of the same equal rotations. And so therefore, if we could just
Looking
find in
at
the
it,
paper, or if someone knows what are the lengths for an arbitrary one of these tiles in this interactive,
on the unit one it is.
So that's actually easy. That's if you just go to, let me find the thing that I'm looking for. It tells you those ratios of the line segments. Um,
I
that's
think the
that's why
picture was
tile
just
1 1 is
Yeah,
called
yeah.
tile 1 1 is because the ratio
substitute
is
for
like
the
1
unit
to
since it would
1.
have the same
The other
properties.
tiles on that
But
slider
I think the
should
easy way to
have
do
just
this is
the
just
number.
add up
for
just
something.
assign the lengths to be x and y, and then just
we
add up,
counted
just
them.
compute the each of the 6 directions in
That's
terms of
that's
x
the
and y, and
N0.
then just have the answer generally.
So yeah. So this picture,
On the unit, it is the same as the length.
No, yeah. The picture you
As we change the slider, no.
Yeah.
yeah. The picture you have is like 1.73 for the
I
longer
wonder if it's
ones
the
and
3.
1 for the
Is it
shorter ones.
the ones that are in the orbit that
Correct. Yes. On that.
change
Yes.
together? Or
Well, how many are the longer? Wait, so what directions are the longer and shorter ones in this? Like, I haven't thought.
Longer is horizontal, a sixth of a turn and a third of a turn.
Like,
Yeah.
basically, do they mesh well with the?
I believe. Sorry, I said
I'm
that wrong.
satisfied with the matrix solution.
Yes, because as you move the slider from the center, tile 1-1,
Oh,
you move
yeah.
it off to the other side. You can see that only every other
In that
rotation.
case,
so the less common
stays
I
one
think I'm
is
probably going to drop off.
but the
quarters
other
of the
ones shrink
length
off to 0. And then it's the
of the more
opposite
common?
3
Yeah.
that are
Thank
present
you.
on the opposite side of
I
this.
appreciate it. Yeah, it was
So
an
so
interesting puzzle.
the sliders at the far ends are like 90-degree rotations of the available
Bye-bye.
orientations.
Okay, so what we need then is we need to find one where
Yeah, I do have to stop, Craig.
instead of like 1 times 6 and 1 times 8 giving a ratio of 4/3, we need like more
it'd
than
just be the
1 times 6
ratio
and less
between
than 1
them.
times 8 giving a ratio of 1,
Like-
right?
Yeah, that's just
Yeah, I'm trying to figure out how the slider works because it like some numbers go like sometimes they're both above 1. It's a very weird slider.
Correct. So on 1-1, the tile 1-1, the vertical and horizontal segments are both the same length. It's 1.37 units or whatever. And then you move to the hats, and now one
Oh.
of those is a unit length, and the longer one is 1.7.
I see. It preserves the sum of their lengths. Okay. Yeah, because the sum of their lengths is 2.73 ish, regardless of where on the slider you are. Okay.
Correct. Yes. Yes.
Woohoo.
So now it's just like arithmetic I don't want to do.
Yeah, thanks for the problem.
Yeah. I'm very satisfied. I think this was delightfully enlightening. I'm very glad that you guys all participated. And I did just get an answer to this question that I've been wondering about for a year now. A ratio of 4-3 is crazy.
glad I could help out.
Yeah, I should
Brilliant.
get some sleep.
Thank you all for joining. Any old time. Thanks for helping out. All right, I am headed out as well. Take it easy. I'll see you on the next one.
Forget to stop